Hello, my name is Josiah Wong, and this is my project for CS236, and we're exploring KL Divergence as a detection method for adversarial attacks. And so quickly, let's talk about what are adversarial attacks. Essentially, this is just any perturbation you apply to an image that would cause a classifier to misrepresent an image's label. So the problem with this is that even really small perturbations can suddenly cause a classifier to change its labeling of an image. So on the right here, you can see even a single pixel change causes the classifier to think that this 7 is a 9. And so this project looks at finding a novel way to detect these adversarial examples. And we're going to be using a semi-supervised variational autoencoded model and deriving some KL divergence metrics in order to detect examples on the MNIST datasets. And we're going to be using white noise attacks, fast gradient method attacks, which essentially backpropagate through the classifier's gradient in order to optimize each pixel's perturbation, and pixel attacks, which are low-order perturbations of individual number of pixels within a given image. And so here are the proposed KL divergence metrics that are going to be used to detect anomalous examples. There's two of them. First one is delta, which essentially is the relative KL divergence of an incorrect label paired with an image relative to its true label, and then psi, which essentially sums across all the incorrect labels given a specific image and returns the normalized value. And so our postulation is that we expect that abnormally high delta and psi values would represent an abnormal or perturbed image. And here are the results from our experiments running with all the attacks, and we see that it performs the best with low perturbations and begins to deteriorate a bit as the intensity increases. The important thing to note here is that intuitively we can see how our detection method is actually working, and so you can understand how these are the clean distributions that we expect for psi and delta. And then these are the successful adversarial attack distributions between the different attacks over here on the right. And you can see how there's a distinct difference in both its mean and its shape. And so the detection method effectively thresholds the value at the upper end of these clean distributions, which simultaneously intersects with the lower end of these adversarial distributions, thereby preserving most of the clean dataset while detecting most of the anomalous datasets. And so the key takeaways is that we have the best performance against black box attacks, and while it's being outperformed by a lot of other detection methods, this is both very scalable and very low in terms of computational time intensity during test time. And so this could make a good addition to a pre-existing suite of defenses. Future work can look at more complex datasets, which have already had some preliminary tests conducted upon it, but with poor results. So future work has to be done there. Thanks for watching.